Okay, we're starting chapter 2 now, and essentially we've looked at a lot of applications of integration, arc length, average value of a function, work, fluid force, center of mass, all that stuff. But essentially, while we were looking at new applications, once we had a formula and had plugged in a function, the integration was actually incredibly easy. Now we want to kind of go in the opposite direction, and we're not going to look at applications, but we're going to look at, we'll say, harder and harder or more challenging integrals. Right now, if I have the integral of something that's polynomial in nature, I can use a power rule and integrate it. I know I have u substitution and integration by parts, so if I have integrals that can be solved with one of those, I'm good to go. But the ultimate goal of this class is to be able to integrate everything. So we want to start looking at integrals that we don't know how to integrate and then say, how do I integrate them? So the first class of integrals we're going to look at today are trigonometric integrals. And from a student perspective, from a problem-solving exam perspective, essentially the way it works is you have a list of tricks: power rule, integration by parts, u substitution, the trick we'll use for trigonometric integrals. And you just kind of learn all the tricks just like you do for derivatives. And then when you have a problem to solve, you just run down the list. Will this work? No. Will that work? No. So you want to learn each of these tricks and then be able to apply them as as a grad student I knew years ago said, kind of tools in your mathematical toolbox, where each problem you pull out the trick that you need. And the idea here is, I have a bunch of these set up that I want to solve. So suppose I have this. The integral of sine cubed x cosine to the fourth of x dx. And if you think about this, it's clearly not polynomial. That trick is out. U substitution. Well, if I say use the u substitution, like what's my u going to be? Is it going to be sine or cosine? And then both of them are raised to powers, and maybe that causes a problem. Integration by parts, I could let one be u, the other be dv. But then since they're both raised to powers, when I say either integrate or take the derivative of either of those trig functions raised to powers, things are going to get messier and messier. So that doesn't work. So we're essentially going to use our u substitution for these, but we're going to use it in a slightly different way. We're going to do algebraic tricks first, or trigonometric tricks actually. And the idea is, well, let's see. Either I have two options. I can let u be sine x, or I can let u be cosine x, because those are the two trig functions that I have. And then, well, if I think about it, if I'm going to use u sine x, du is cosine x. If I use u cosine, derivative of cosine is negative sine x. And then the way it works, in this case, rather than looking at the u, we tend for these integrals to look more at the du and say, if that's the du I need, what will that leave me with? And can I then solve or substitute for what's left over? Meaning right here, if my du is a cosine, I'll just rewrite this. Sine cubed x, cosine cubed x, cos x dx. And now right here, I've kind of separated off, these should have dx's on them. I've separated off my du. So then I somehow have to write all of this in terms of u. Clearly I can write sine cubed in terms of u, that's u cubed. Cosine cubed, there's no way to write that in terms of a sine. There's no identity that lets me go back and forth between sine cubed and cosine cubed. So that's not going to work for me. If I try the same with this, my du is negative sine, so I'll get the integral, I'll pull out a sine. I'm not going to worry about the negative right now. I can just throw it out in front if I need to. But that will leave me with a sine squared x, cosine to the fourth x, and then my extra sine x dx. which is my du right here. Again, I know there's a negative, so I pull to the front. Now, I need to write everything in terms of cosine. That's clearly u to the fourth, cosine to the fourth. Sine squared, there actually is an identity that we know from trig, the Pythagorean identity. Sine squared is 1 minus cosine squared, which I can substitute in, and then I can distribute the cosine to the fourth. Then everything will be in terms of cosine, which is my u. So that's the trick I'll use here. And if you're kind of following the logic, that's how we're going to solve all these trigonometric integrals. Trigonometric integrals are just integrals that only have products of trig functions. We're going to rely on our understanding and remembering all of those trigonometric identities that you were told to remember in trig, and do substitutions. Most of them will involve the Pythagorean identities. There is one other identity that we'll need for some of these, but essentially, I'll look at my integral and say, what do I have? What u's can I use? What du's will I get? And then which of those gives me an integral I can work with? And I will point out, your book gives formulas for all these trigonometric integrals. If this, do that. If this, do that. If this, do that. If this, do that. And as a student, I didn't remember any of them because there were just too many and they confused me, especially when taking an exam when I'm under pressure. So I prefer to just look at the problem and kind of think about what's going on a little bit and understand it. What I mean is, looking at this, I know Pythagorean identities can relate quadratic terms, which means if I have an even number of cosines, I can write those as an even number of sines. If I have an even number of sines, I can write those as an even number of cosines. They can go back and forth. So what I really care about is the extra terms floating around. In this case, there's an extra sign floating around, which tells me that will be my du, which then tells me my u. So for this, I'll rewrite it as u equals, like we said, cos x du is negative sine x dx. Now, when I rewrite this, I know my du is going to be negative sine. Right now I'm just going to worry about the sine. So I'll separate that off. Sine squared x, cosine to the fourth x, sine x dx. Now we write all of this in terms of cosine, so it becomes the integral of 1 minus cosine squared x, cosine to the fourth x, sine x dx. Which is then when I distribute cosine to the fourth of x minus cosine to the sixth of x, sine x dx. Now I'll apply my substitution. And in this case, this becomes, I know I need the negative. For sine x dx, I divide the negative over here. So I'll pull that to the front. Negative of the integral, cosine is u, so u to the fourth, minus u to the sixth, sine x dx is du. Now that's just a simple integral. Negative of u to the fifth over 5 minus u to the seventh over 7 plus c, which will then distribute the negative in, which will flip everything around. I'll get u to the seventh over 7 minus u to the fifth over 5 plus c, and then I substitute back. U is cosine, so I get cosine to the seventh of x over 7 minus cosine to the fifth over 5 plus c. And again, I would point out, the integration part is actually incredibly simple. Just a u substitution. It's just algebraically taking this integral like this and finding a way to rewrite it to something that can be easily u substituted. So we're going to go through a few more just to see if we can kind of get the trick and how it works. So next up, suppose we have the integral of cosine cubed x over the square root of sine x dx. And in this case, we know we're going to use a u substitution. And now we know from our understanding of u substitution, denominator and thing inside of radical are always going to be my u. Which then if I kind of scribble on the side, that means my u is going to be sine x. So my du is going to be cos x dx. So now I just pull out my extra cos x, see what's left over, and go from there. So I get the integral of cosine squared x over the square root of sine x cos x dx. There's my du. Now I rewrite this in terms of sine. So I get the integral cosine squared is 1 minus sine squared x all over square root of sine x cos x dx. Now here, this can look really messed up, but that's 2 terms over 1 term. Just rewrite the whole thing. And I get 1 over root sine x, forgot my integral symbol, minus sine squared over square root of sine x, which is sine to the 1/2, is 2 minus 1/2, which is 3/2. So that's sine x to the 3/2. Here, we'll just rewrite this now, since I know I'm writing this as a power. This is sine x to the 1/2. It's in the denominator, which means I can rewrite it as sine x to the negative 1/2. All of that times cos x dx. Now I'll do my substitution. And it becomes the integral. U is sine, so that's u to the negative 1/2, minus u is sine to the 3/2. Cos x dx is my du. Now just do the power rule. Let's see, raise the power, negative 1/2 plus 1 is positive 1/2, so it's u to the 1/2. Then you divide by 1/2, which is the same as multiplying by 2, minus u to the 3/2, raise the power by 1, 3/2 plus 1 is 5/2, divide by 5/2, which is the same as multiplying by 2/5, plus c. And then my last step, substitute back, and I get 2 times u, which is sine to the 1/2 x, minus 2/5 sine to the 5/2 x, plus c. And again, the integral part is actually really trivial. It's just the setup and understanding, and once we understand that it's a u substitution, we have rules that you learned in Calc 1 for how to set up a u substitution. We're applying them here. The only added trick is throwing in these Pythagorean identities to rewrite the integral. But there are other trigonometric integrals. Suppose I have the integral of cosine to the 4th of x dx. And now here, if we think about it, I only have one trig function. I know I can rewrite cosine in terms of sine as 1 minus sine squared. But then those signs that I write will still be even. I won't have an extra one like we did with the odd sine or the odd cosine. And if I don't have the extra one, then the u sub won't work. So my u sub trick and a little bit of algebraic manipulation won't work. So I need to do something else. And here, I have to rely on another identity that you're supposed to remember from 172, trigonometry. Power reducing identity. Sine squared of x is 1 minus cosine of 2x all over 2, and cosine squared of x is 1 plus cosine 2x all over 2. The two power reducing identities. I can power reduce that. So for this one, what I want to do is, first I rewrite it as cosine squared x squared dx, because the power reducing identity works on the quadratics. Now, reduce this, and it becomes the integral of, I'm going to rewrite this as two separate fractions. 1/2 plus cosine 2x over 2 squared dx. Now, I need to solve that. But the problem is, well, now I have a sum of two fractions squared out, and how do I solve that? Here, FOIL it out and see what you get. So if I FOIL, I get, all of you can FOIL, so if I FOIL that, I get 1/4, 1/2 times 1/2 is 1/4, plus cosine squared of 2x, if I square that, cosine squared of 2x over 4, plus, now I multiply both of those twice, so I get cosine 2x over 4, but I get two of them, so 2 cosine 2x over 4 dx. And that's just doing the FOILing out, which all of you can do. And now I guess if I rewrite it a little bit, 1/4 plus, I'm going to put that term second, 2 over 4 is 1/2, so cosine 2x over 2, 1/2, 2/4, plus cosine squared 2x all over 4 dx. And now if you think about it, that's 1/4, that's an easy integral. Cosine 2x over 2, that's a regular trigonometric integral, not a big deal. Here I still have a cosine squared, and I need to integrate that, but now I actually know the trick. Reduce the power here. Power reducing identity again. And if I then rewrite this, I get the integral of the 1/4 stays the same, cosine 2x all over 2 stays the same. Here, keep in mind, I'm going to write this separately just so we can see the algebra. This is 1/4 times cosine squared 2x, if it helps you visualize it, which is then 1/4 cosine squared 2x becomes 1 plus cosine 4x all over 2. Keep in mind in the identity, cosine squared of x becomes cosine 2x. Whatever is in here gets doubled when you use the identity. So since this was 2x, it becomes 4x. This then simplifies to 1/4 times 1/2 plus cosine 4x over 2. Now over here, rewrite it and distribute it. So I get 1/4 times 1/2 is 1/8. It's not very straight. Plus cosine 4x over 8 dx. Now, if I just rewrite it, 1/4 is 2/8 plus 1/8, that's 3/8, plus cosine 2x all over 2, plus cosine 4x all over 8 dx. And now, while it took a little bit of algebra and trigonometric identities to manipulate that, that's a nice simple integral. Antiderivative of 3/8 is 3/8 x. Antiderivative of cosine 2x over 2. Antiderivative of cosine is sine, the inside stays the same, and then we divide by the derivative there, which is 2. There's already a 2 on the bottom, so that becomes 4. Antiderivative of cosine is sine, inside stays the same. Then we divide by the derivative there, which is 4 over 8 is 32, plus c. And I get a nice simple answer. And let's see, there was one more I wanted to do. Yes, right there. Okay, good. But the point here is, from a problem solving perspective, if you have two trigonometric functions, see which one is the extra one. And then once you have the extra one, that will usually dictate your u substitution. Then you'll just have to use trigonometric identities, usually the Pythagorean ones, to write everything in terms of one trig function, your u, and then do the u substitution and you're good. If you end up with trigonometric integrals with only one function raised to a power, there's different things you can do. One thing you can try, especially if all the powers are even, is power reducing identities. They just tend to take longer because of all the algebra involved with the identity. But so far we have restricted ourselves to sine and cosine, and all of you understand, because you've taken trig, if I have other trigonometric functions in my integral, you can try to rewrite everything in terms of sine and cosine and then use this. But you can also try other things. So suppose I have this. The integral of secant to the fourth of x tangent cubed of x. And let me just make sure I wrote down the one I wanted correctly. Yes, I did. Good. And I can try to write this in terms of sine and cosine and see what's left over. Or I can try to use the same trick in terms of tangent and secant. And by extension, if I had cosecants and cotangents, I could try to do the same thing. The only difference here is, keep in mind my derivatives for sine and cosine are straightforward. Sine, cosine, negative sine. Here, well, with tangent and secant, they're a little bit more involved. So just for review, if f of x is tan x, f prime of x, the derivative of tan is secant squared x. If f of x equals secant x, the derivative of secant is secant x tan x. And we understand also, just like we did before, we have the Pythagorean identities. 1 plus tan squared of x equals secant squared of x. So we still have this quadratic relationship, so I know I'm looking for the extra term, but in this case my extra terms are a little bit weird. So these can be a little bit different, but still do the same thing we did with sine and cosine if we're unsure. Either try to memorize complex rules, or just try both of them. Generally speaking, one will work, the other won't. If they both work, solve it both ways and make sure you get the same answer. But, well, let's see. If I used this one, then u would be tan, and this would be my du. So then if I check over here, that would give me, I'd have to pull out a secant squared, so I'd be left with secant squared x, tan cubed x, secant squared x dx. And that would be my du. And I know tan cubed, tan is my u, secant squared, I can write as tan squared using the Pythagorean identity, so this one works. If I try the other one, my du is secant tan, so if I pull that out, I get secant cubed, because I pull out one of them, tangent squared, because I pull out one of them, and then I have my secant x tan x dx on the end. All of this is my du. My u is secant, so that would be secant right there. That would be my u, and I can write tan squared in terms of secant squared. So here I can actually go either direction, and both of them will work. Just because I happen to write that one first, I guess we'll do that one. So, make it neater. So I know I'm going to use u equals tan x du equals secant squared x dx. So this I will then rewrite, I'll pull out my extra term as secant squared x tan cubed x secant squared x dx. Now, Pythagorean identity, I want everything in terms of tan, so I'll rewrite secant squared, and this becomes the integral of 1 plus tan squared x times tan cubed x secant squared x dx, which then becomes the integral, if I distribute, tan cubed x plus tan to the fifth of x, parentheses, secant squared x dx. Now apply my u substitution. And I get the integral of tan cubed, which is u cubed, plus tan to the fifth, which is u to the fifth, secant squared x dx is just du. And the integral is simple. That's u to the fourth over 4, plus u to the sixth over 6, plus c. Then substitute back, u is tan, so I get tan to the fourth of x over 4, plus tan to the sixth of x over 6, plus c. And again, I do stress, and this will actually become apparent as we learn other tricks here, the tricks are mostly algebraic in nature. And by that I mean, take an integral, do some algebra on it, using identities, algebraic tricks, things like that. Then ultimately get to an integral that's easily solvable by way of u substitution, maybe an integration by parts. The trick from your perspective is to be able to look at the integral, identify it, and say, yeah, that's not a power rule, that thing's out. Definitely not using integration by parts there. U sub will work, but in order to use a U sub, I have to come up with a U and a DU, which then causes me to rewrite everything algebraically. So there's kind of an algorithmic approach here to how you want to solve these. Set up, figure out what type of integral it is, which dictates the algebra you do, which ultimately arrives at the solution. The other thing I will just point out, here I only did indefinite integrals, all the wonderful plus c ones. Can you do this with definite integrals? Yes, you know that, just like in Calc 1. The only difference would be, at the end, I'd plug in my limits and be good there. I just wanted to stick with indefinite ones here for the video. That should be enough. Like I said, are there other tricks that can arise as you do these? Yes, maybe sometimes I have to use a power reducing identity. It comes with practice. You can try to memorize all the rules that are listed in your book, and if you can memorize them and keep them straight and use them on any individual problem, that's fine. Personally, I prefer just understanding the trick of what's going on, a U substitution, algebraically manipulated, and then just looking at the problem and saying, okay, what am I going to do? Everything either tangent or secant, check both possible U's, this one works, do everything from there. But I understand there are different ways to think about this. This is just the way I prefer to do them. If you have any other questions, want me to do more examples, whatever, feel free to email me or let me know, stop by my office, not a problem.